All right, thank you. All right, so today what we're going to do is we're going to shift gears just a little bit. This is just for one lecture, but I want to talk a little bit about sort of a higher level view of where some of the stuff that we've done in this class fits in. So, and particularly, this is something that was asked a month ago, or a little over a month ago. The question always comes up in optimal control: where does optimal control fit into control systems as a whole? Because it seems like it's a completely different subject. We're doing all this stuff with calculus of variations. We're solving problems with numerical methods. Where it doesn't fit the classical feedback control. We're going to design a compensator, and we're going to do Laplace transforms and all the stuff that you people have learned in other classes. And so I just want to take a few minutes. This may not even take like all the time today, but it's a worthwhile topic to go through, which is that in any control system, we have the following components. Okay, so what are these components? So these components are, one, we have a plant. Now, this is would also be construed as the dynamics of the system, or a model for the dynamics of the system. We also have what's called a measurement, something that takes measurements. So a measurement system. And this, in the case of an aerospace system, would be called navigation, although it's not really necessary that you call it navigation. We also have control. We have estimation. And then we have what's called reference signal generation, which, in the case of an aerospace system, we would call that guidance. Now, one of the things, when you actually look at, I'm going to draw a picture here in just a minute. So, one of the things that there's a misnomer about this concept of guidance and navigation in particular. Those two things, the terminology is completely misused. All right. So if I was to ask you the question, notwithstanding what I put on the board there, what would you say guidance is? What is guidance? Think about it. Forget about math and all this, block diagrams. Just think in human like life in general. What is guidance? You use the word guidance in a lot of contexts. I'm lost. Please give me some guidance. What's that? Where you want to go. All right. So guidance is a path that you want to go down, or a potential path that you want to go down. So what's navigation? Where are you? Right? But those terms don't get used that way. When you say, don't you do this all the time? You do this. A lot of you probably have these units, right? Do any of you have a TomTom or a Garmin GPS unit? It's a global positioning. It's called a GPS navigation system, right? That you stick in your car. It has nothing. What happens when you turn on the turn-by-turn directions on a GPS navigation system? What's happening? What do the turn-by-turn directions do? What are they giving you? What are they giving you? They're giving you guidance, right? So it's actually a GPS guidance system. It's not a GPS navigation system. If you just stood there at a point on the Earth and said, where am I, and just looked at the unit, and the unit told you were at this many degrees latitude and this many degrees longitude, then that would be doing navigation. But as soon as you turn on the turn-by-turn directions, which is what most of us use GPS units for, to go somewhere, it's doing guidance for you. But they don't call them GPS guidance systems. You know why? Because if they marketed them as GPS guidance systems, there'd be all kinds of other issues associated with it. Nobody would buy them. I don't want guidance. I want navigation, right? It's not. You're not getting navigation. You're getting guidance. So you say, well, I'm going to navigate my way through the streets. You don't navigate your way through the streets. You guide your way through the streets, right? Navigation is the measurement process, right? It's saying, I know where I am now. Now I'm going to decide how I'm going to guide myself, right? It's not, I'm navigating. This term navigation is used completely incorrectly. That's not navigation. Navigation is the process of determining where you are and what your velocity is. That's navigation, right, if you're thinking about an object. Okay, so now let's put this together. Now, the dynamics are pretty obvious. That's the system that you're trying to control. But the other thing that's confusing here, so I just got through talking about guidance and navigation. There's also an issue, though, with control and guidance. What's the difference between control and guidance? So what's control? What's that? Okay, well, it'll be a little bit more specific. What is control? Now, control is really important that there are two aspects to control, right? One is the fact that you need to tell, so you need to tell a system what you want it to do, and then you actually need to execute. The execution is the actual control itself. In other words, if I have an aircraft and I want to increase its velocity or increase its altitude, I might increase the thrust, right? So I change the thrust level, and the aircraft will ascend and it will go faster, right? So why the aircraft ascends is because you put more thrust on it. Means you have a higher velocity relative to the air, which means you generate more lift, which means the vehicle goes up. That's why the vehicle goes up. It's one of these oxymoronic things about flying an aircraft, which is that if you increase the thrust on the aircraft, it does not just increase the velocity, it also increases the altitude. Of course, if they're downward lift, you're kind of screwed because the aircraft will crash. But that's a different story, right? We don't want that. So the thing is that there's the actual the actuation itself, which is actually hardware. It's not software. And then there's telling the system what it is that you want it to do, right? Now, when we do this, in reality, this is what we're doing. So here's the deal. So now I'm going to start drawing a picture here. And I'm not sure this picture is going to fit on one board unless I draw everything small. So I'm going to try to draw everything small. So here's our plant, okay? And put that in the box. This is dynamics. No. So I've got that. Now, what comes out of this and what goes into it? That? Yeah, no, you can't just say output and input. What is the output? What is the input? The input's the control, okay? So the input, I'm going to label the control as U. So the input is U. What's the output? What describes the dynamics? What's that? Now, what describes the actual dynamics itself? How are dynamics generally described? We've been doing it for 12 weeks, 10 weeks. How do you describe dynamics?
Differential equations.
What's that?
Differential equation.
What's that?
Dynamics are described
By differential equations. So what should come out of here?
different states.
The state should come out? Should the state come out?
Changing the state.
What's that?
The change.
What is the differential equation? If you take a nonlinear differential equation, first order differential equation, it's x dot equals f of x z of t, right? So the dynamics are described by f, right? F tells you what the dynamics are. If I input into this, what do I need? What do I need in order to tell you what the state is? I need to know x and I need to know u, right? So u is one thing that goes in. I'll deal with the x part in a minute. What comes out of this thing is x dot. Now what I need to do is I need to pass this through an integrator, and this gives me x. All right? I have to integrate it once in order to get x, because if I have a first order system, right? But what is true about most systems? Can I actually measure the state? No, I can't measure the state in general, right? What I can do is I have some function, which I'll call navigation. Well, this is bad. I'm running out of thing. I knew it was going to run. These boards aren't wide enough for this. So we'll put it down here. Here. Navigation. And this is also what I call measurement. So when you measure something, you don't get the state, you get this thing called y, whatever y is. Y is some function of the state, but it measures something, right? So now I have y coming out. This board is going to get cluttered in a bit here, so I've got to be real careful here. So I've got control, and I've got this output. So I can't measure the state. So how am I going to get the state? How does one get a state? I can't get the state. I can only get a function of the state. My device doesn't measure the thing I actually want it to. It measures a function of the thing that I want it to. But I need to be able to figure out what the state is. So how am I going to figure out what the state is? You have to estimate the state, right? So the estimation of the state goes down here. So here's estimation. What goes into state estimation? Y and U, right? I need to know both the output and the control in order to be able to determine what the state is. What comes out of this is an estimate of the state, which I'll call x hat. It's not the state. So I'm not done with this diagram. Now, U has to be generated somehow, right? So where does U come from? Comes from a controller. All right. So the controller, what is the controller going to generate? So here I'm gonna put a summation here just because I'm gonna need it in just a second. So what I need is somehow over here, I need to do something with this to generate myself a control. What's going to generate the control for me? What's that? There's a control law, right? So somewhere over here there has to be a controller, right? So what goes into the controller? What's that? Does it? Does X hat go in? Ah, yeah, there's got to be another. Now there's got to be another error signal here, right? Now, see, this is getting complicated, right? So look, there's a lot of stuff going on in here. But down here, I'm going to put guidance just for a second. I got to block it off separately. Okay, I've got guidance. What goes into guidance is an estimate of the state, but I'm going to put a switch here. The switch operates every t units, right? So every time the switch operates, I generate a new guidance command. What comes out of guidance are two things. I generate myself what's called a reference signal, which is a reference state. I also generate myself a reference control. Now, I'll figure out what these things are in just a second. But the reference control and the reference state have to be used together in order to be able to do the rest of this. So what should the control signal be based on? In other words, if I was on the reference, right, what should this controller generate for me? Zero, right? If I'm absolutely on the reference, I shouldn't need to add anything to it, right? So what this thing is going to generate for me is actually what's called delta U. It's going to be the difference between the state estimate, which is coming in here, right? So this is x hat. And it's got to have this reference in here, which is coming in here too. So, but the thing is, which way this is done, it doesn't matter, but it's actually going to be a negative sign. So it's going to be x minus x hat that's going to come in here. This is going to be delta x that's actually going to come in here. So delta x comes in and delta u goes out. But the problem is, I still haven't figured out how to deal with the control. The control is going to be generated from two things. It's going to be generated from this delta u plus this reference, which is going to generate for me the full control, right? Because the dynamics needs the full control in order to be able to use it. It needs the reference control plus the error or plus the perturbation in the control due to the fact that the state estimate and the state itself and the reference state don't match each other. Now look at this diagram. Okay, this is hard to read because the board is, if I could spread it out over two boards, it would be a lot easier to read. But if you look at this, there are two parts to this. Guidance has nothing to do with control. If I just said, I'm going to generate a reference signal somewhere, I don't care where I got it from, generate it once and just use it throughout the entire process, that is guidance. Then guidance would be done once at the very beginning of the process, and it would never be done again, right? But that's not the way you do guidance, right? You do this all the time. You don't realize you do this. Let's suppose you're driving somewhere, and all of a sudden in the middle of what you're doing, you realize, you know what, I'm a little bit lost. I need to correct. What's that called? You got off course. Now you need to do a correction. We have a term for that in the aerospace industry anyway. We do, but I mean in general you probably have used this term yourself. You're doing a mid-course correction, right? You're in the middle. You know you need to be on some path, but you're way off that path, so you're going to do a mid-course correction. So what the mid-course correction is like, well, I did my estimate of where I am. It's nowhere near where I want to be, so I'm going to solve this guidance problem again to get me from where I am to the end, and I'm going to use that as my new reference signal until the guidance computer tells me I want to generate a new reference, right? So I do this over and over again, but I only update the reference every time that switch gets closed. So when the switch is open, the only thing it knows is the last time I did this is the last solution I have. That's the one you told me to use, so that's the one I'm going to use. If I close the switch, I'm going to regenerate the reference, and from that point forth, I'm going to wind up using I'm going to use the new signal. So you can see from this diagram that guidance and control are not the same thing. Guidance is typically what's called outer loop control. Control is actually what's called inner loop control. When you take a control systems class, when you learn things like automatic control with Laplace transforms, you're learning inner loop control. You're not learning outer loop control. So where optimal control fits into this is down in here. Because in this block, I have the choice of how I'm going to design my reference signals. I can design those reference signals any way I feel like designing the reference signal, right? But generally speaking, you want to design a good reference signal, right? So if I say I want to design a good reference signal, what does that mean? It means that I want it to be something that, if it could be in theory, minimizes or maximizes some performance index, which gives me the best reference signal, right? Best is always dependent upon what you're calling your cost, right? If my cost or my performance index is some function, I want to make that function as large or as small as possible, and I want to satisfy all my system constraints. That's the best reference signal I could possibly generate, right? Given the cost function that I've posed. And that becomes optimal control. So optimal control is actually optimal reference signal generation. It's the concept or the process of determining a reference signal based on the fact that you want to minimize or maximize a functional, subject to a bunch of constraints. Some of those constraints include are the dynamic constraints of the system. And the whole concept of it is that by generating as good a signal here, you make your control, or you allow your controller to process the information in such a way that the path that's actually subtended by the system is as close to that best thing that you said you wanted it to be by the fact that you solved this particular optimal control problem. So that gets down to, optimal control, if you want to call it that, is equivalent to saying optimal guidance. Now, the thing that's kind of cool about this is that you don't have to resolve this problem if you don't want to. You could just solve it once offline. You could say, at the very beginning, before I ever do whatever it is I'm going to do, I'm going to solve this problem, and I'm going to generate myself a reference control and a reference state. And I'm never going to solve the problem again. That means you're never going to close this loop. And if you never close this loop, you're doing what? You're doing an open loop, right? An open loop is what we've been studying for the last 10 weeks or 8 weeks. We've been figuring out how to generate open loop solutions to the optimal control problem with no feedback whatsoever. There's no correction going on. We're never resolving the problem. But in principle, if I had new information, I could resolve the problem, right? I could say, well, this is the problem I started solving, but then as my object started to move, it got bumped off the course that I thought it was going to be on, and now at some point later in time, I'm going to use those initial conditions, and I'm going to resolve the problem from that point to the end to generate myself a new optimal trajectory that corresponds to the optimal control problem that starts at that particular time based on the state estimate that I've gotten from some estimator that has told me what it thinks my state is based on the fact that I'm doing some measurement, which is a function of the state, right? So this whole process, this is navigation. Navigation has nothing to do with guidance. You can do navigation completely independent of guidance. In fact, you normally do. Navigation is the mere process of measuring. I stick a thermometer in your mouth and I say your temperature is 98.6 degrees. That's navigation. Doesn't tell me what to do. The treatment is the guidance, right? It's like if you say you've got a fever, say, I'm really feeling sick. You stick a thermometer in your mouth, the temperature is 101 degrees. They say, well, I got to do something about that, right? What can I do? I can rest. I can drink lots of fluids. I can take ibuprofen. I can take, acetaminophen. I can take aspirin. I can do all kinds of different things to help me reduce the fever. That's guidance. That's not navigation. That's guidance. You're not navigating your way to feeling better. You're guiding your way to feeling better, all right? It's a misnomer to use the terminology navigation when you mean guidance. And when you say guidance, you shouldn't be meaning navigation, vice versa. Either way, it doesn't work. The main thing is navigation is all about measurement. And it's a subject that, in and of itself, is like a pretty profound subject. I mean, it's remarkable how difficult a problem navigation is. Navigation may be the most difficult problem in all of aerospace engineering. I don't think that's an understatement. It may be the most difficult problem because no matter what you do, you're always going to have errors in your system. It doesn't matter what you do. You will always have errors. And if those errors get large, which they can, then you have to have a way of being able to figure out, well, in the presence of large errors, I still need to know what my state is, right? My state estimate still has to be pretty good. So you don't always have these wonderfully perfect instruments that can say, hey, you know what? I know exactly what your position and your velocity is, and you don't need to do any state estimation. That would be great if you didn't need to do any state estimation. But the reality is you generally do because you have to filter the measurements that you get, right? So this is the whole block diagram that comes out of this process. I really wish I could spread it on 2 boards, but I don't think it would fit too. I don't think it would show up too well, even though on the screen it looks like it would. But I need a full 2 board. So this concept of optimal control. Now let's go back over here for a second. Now, if you start looking at the things that we've done in this class, because the last topic I'm going to do starting next week is dynamic programming, and it's kind of disconnected a little bit from the stuff that we're doing now. So I wanted to take the time to do this first. If you think about what we've done, we went through all this mathematical theory, derived all these optimality conditions by using the calculus of variations, and we came up with these necessary conditions for optimality. All that told us was, if we have an extremal solution, it must satisfy these conditions. And then we all realized that pretty quickly that there are only a small class of problems for which you can actually solve those necessary conditions. Most of the time, you can't solve them analytically, and then you have to resort to numerical methods. And if you use numerical methods, if you're trying to solve those necessary conditions, they're not very easy to solve. So then we went down the path of trying to learn other types of techniques in order to be able to solve the optimal control problem. In all of those cases, what we were trying to do was we were trying to take this problem and transform it into something where we could get an approximation to the optimal solution to generate ourselves a reference trajectory and a reference control. Now think about this, if you think about this in the context of a control system, in order to be able to apply this in such a way that every t time units you close the switch, whatever it is that you're doing in here has to be solvable fast enough that you can actually get a solution, right? I mean, clearly, if you're sitting there in MATLAB and you're using something like fmin-con and you got some complicated optimal control problem, it's going to take a while to get a solution, right? For any reasonably complex problem, you're going to be sitting there saying, I'm not going to get a solution to that thing very quickly, right? It may take hours, it may take weeks, in which case it's kind of useless to try to resolve it, right? Because if you have a vehicle flying through the air, it's not necessarily going to wait for your solution 6 hours later before it can say, oh, you say, here's my solution, and you say, well, I've already landed my vehicle, right? So I landed a long time ago, right? So that's not very useful. So it has to be solvable fast enough to be able to do this. Now, in a lot of applications, you don't need to solve this problem that fast. Some applications you do. If I've got something like the space shuttle re-entering the atmosphere, that's a hypersonic vehicle re-entering the atmosphere with 7 astronauts on board. The whole duration of the entry takes about 15, 20 minutes, and maybe not even that long. So you can't have a guidance computer that's going to be solving something really slowly. It's got to give you the control very, very fast, right? So what they did in the old days is they don't do this. They do this still, but they used to do it a lot more 30 or 40 years ago, is they would come up with simplified models for these problems, and they would say, is this a reasonable approximation to the problem that I really want to solve? I don't know if it's a reasonable approximation. But they would do a lot of physics would be involved in this. They say that I know the optimal solution should really do this, but can I generate a guidance law that gives me something that's close enough to what that thing would do that it doesn't matter that it's not off, that it's off by so little that it doesn't make a difference. In fact, the classic example of this is a launch vehicle ascent. A launch vehicle ascent, it turns out, they never solve the optimal control problem. There's no reason to solve the optimal control problem because it turns out that this profile, this classic profile of a launch vehicle, all launch vehicles do this. You can look this up in a textbook. They all do this. Is that they're sitting on a launch pad, and they fire vertically, and then they pitch over, and they do a gravity turn, and then then first stage drops, and then they fire the second stage, and then that drops, and then they fire the third stage, or however many stages they got, and then finally they get to the last stage, and they have a payload fairing that opens up. It's got the spacecraft on board. It does a final burn, puts you into the orbit. That's a classic thing. Each of these segments, the control is something very, very simple. What they're doing is they're doing a pitch profile. They're basically just steering the vehicle by pitch, because they're doing they're not yawing. You don't want to yaw a rocket, because you yaw a rocket, the rocket's going to go straight into the ocean. You want to keep it pointed straight along its nose the entire time. So they're doing something like this. And it turns out that each of those segments of the trajectory, they approximate the control as being piecewise linear. And you say, well, piecewise linear, that's pretty stupid. I mean, that's like, how close to optimal can that be? Turns out it's really close to optimal, because the problem is so simple that there's not much that needs to be done. So they can just do constant pitch rate here, constant pitch rate there, constant pitch rate here, and they just do that sequence of constant pitch rates, and they decide where they're going to break these pieces up in such a way that it has something naturally to do with the different phases of the vehicle flight. So that's how they do it. It's a very simple thing that they're doing. So in principle, you could do this without anything really fancy, without any kind of really fancy optimal control software, because you've got a piecewise linear control, and if you have a piecewise linear control, you can do that with direct shooting. So direct shooting is the classic way that launch vehicle ascent problems are done. They're all done with direct shooting, because it works really, really well. Now take a more complicated problem. Let's suppose you've got a spacecraft in orbit, and you want to be able to reorient the body. Well, reorienting the body actually turns out to be a significantly harder problem than launching a vehicle in terms of the type of control that you need to use. You need to use a much fancier control. If you want to, say, do a minimum time reorientation maneuver and get the orientation of the body from one orientation to another, if you want to, like, say you got a telescope in space, like Hubble telescope or something, when it gets deployed, there has to be a maneuver that actually puts the telescope in place so it can actually do the imaging that you want it to do. So in order to do that, you have to have a much more precise control law to get it into the right orientation, because if it's in the wrong orientation, it's not going to take the measurements of the thing you want it to take measurements of, right? So there, the control becomes a lot more critical. So there, they actually design things much more closely based on approximations to solutions of optimal control problems if they're interested in some sort of performance index. And in a lot of spacecraft maneuvers, they are. They either want to do this with minimum time, or they want to do it in minimum fuel, because they only have a certain amount of fuel on board, and they don't want to use any more of it than they need to in order to be able to reorient the body. Because they may have to do multiple maneuvers throughout the life of the body. But in any case, all of these things ultimately get down to approximations to solutions of optimal control problems, where the approximation is something that is tractable, that can actually be solved fast enough to be able to generate the command that they want to generate. So they make all kinds of approximations. And those approximations are usually good enough that they get a solution that's close enough to to the performance that they want, that they don't worry about the rest of it. So optimal control provides, though, a framework which you can actually devise ways to do efficient guidance, rather than saying optimal guidance. You say efficient guidance, right? You don't want to do inefficient guidance. You want it to be a good guidance law. But it may not be optimal. And generally speaking, guidance laws are not optimal, because if they were, it would take way too much time to actually generate the optimal controls. Now, today, we have a lot more computer processing power than they did back in the 1970s. I mean, the Space Shuttle Ascent Guidance Computer ran at 25 hertz. I can't imagine that anybody could think of processing anything at 25 hertz. 25 hertz is extremely slow. It is about as slow as you get, right? But you think about 25 hertz, you're like, I mean, your iPhone calculator has a processor that's much faster than 25 hertz, right? So you couldn't do very much with 25 hertz. So they had to devise these really simple things. And there's a really famous paper that was written in 1979 in the Journal of the Astronautical Sciences, which was called Shuttle Ascent Guidance Comparison. It's a really nice paper, actually, if you ever get a chance to read it. And one of the guidance laws that they profile in this paper is what's called PEG. PEG is what classically for the shuttle is called powered explicit guidance. What happens is that as the shuttle ascends, and this is true of all launch vehicles, but it's particularly true of the shuttle, because the shuttle is extremely heavy, is that during the liftoff of the shuttle, there's really no room to do any guidance, because the vehicle is so heavy and it's basically a big rock sitting on the ground. They just need to get it off the ground. So it's like, just get this freaking thing off the ground. So they get it off the ground. And then once they get to a high enough altitude where the atmosphere becomes very rarefied, then what they do is they kick in to what's called powered explicit guidance. What powered explicit guidance is that you want to go to a final orbit. And what it does is it says, what is the velocity that I have right now? What is the velocity I need to get to in order to be in that final orbit? And that gives you what's called delta V. It's delta V. Here's the velocity I have right now. Here's the velocity I need when I'm all done. Take the difference between those two vectors. That's delta V. And so the guidance law says, fire in the direction of delta V. And it just keeps doing that over and over again. And it keeps trying to make delta V smaller and smaller. And it turns out it's really, really close to optimal. It actually follows, if you've looked in Bryson and Ho's book, there's a problem there called, there's a Bryson max range problem, which gives you what's called a linear tangent steering law. And the linear tangent steering problem turns out to be the solution that comes out of what the powered explicit guidance law gives you. Powered explicit guidance is actually linear tangent steering. It's the exact same thing. And so they compute this guidance law based on this delta V, and that delta V turns out to be linear tangent steering. So they're actually solving an optimal control problem. When they did it, they didn't realize they were solving an optimal control problem. What they did was they said, I have a vector, I need to get to this vector, take the difference between those two things, that gives me delta V, and they actually just said, let me just fire in that direction. And it turns out that that actually is equivalent to the linear tangent steering, which is really neat, isn't it? I mean, then they figured it out later that it turns out that from optimal control theory, they could actually determine that it was linear tangent steering. This is all written about in papers. You can find all this stuff. But the thing is that in those days, they didn't have a lot of computer processing power. So they had to come up with really simple ways to do this. But they wanted to be as close to optimal as possible. So as a consequence, they would come up with strategies that sort of intuitively, as an engineer, say, this makes sense. Now the question is, can we verify in some ways that it actually is a good steering law? In other words, we didn't miss something. Did we come up with something really bad? And it works, but it's really bad, right? You don't want something that works and is really bad. You want something that works and is really good, right? So this is how this whole thing works. And this concept all gets back to, what does it mean for something to be good? Well, for something to be good, it has to minimize or maximize some performance index. Implicitly, whether you actually quantify that performance index or not, engineers do this all the time. They look at a solution and they say, that is a terrible solution. I would never want to do that, right? And so they say, well, then they come up with another solution. They say, that looks a lot more like what I want. So even if you're doing this qualitatively, you're still implicitly minimizing or maximizing some sort of performance. You don't realize you're doing it, but you are doing it by the mere fact that you're saying, this is better than that, right? By saying something is better than something else means you have to have some idea what you mean by better, right? So better always has with it this concept that has some sort of underlying function that's going to be minimized or maximized, but you may not always know what that function is because you may not have actually written a mathematical description of it. But even in your own head, you know when you've got something that doesn't do what you want it to do. You're like, I just wouldn't want to do that, right? So you say, I'm going to find another solution because that's not good. Okay? So that is all I wanted to talk about today because that kind of closes this part of the class. And we have a few more weeks, and we can do some other things like dynamic programming. And then as far as your project stuff goes, it'll give you time to ask me questions about your project. So the last topic we're going to do in this class is dynamic programming. I expect to finish it before the actual end of the semester. And then what we're going to do is we're going to go back through the entire class, and we're going to do a review of all the material that we've done from the beginning to the end, so you can see how all of it fits together. And then you'll have your second exam and your project will be good. Okay? So we'll stop with that right